Section 11.3, Surface areas of pyramids and cones. A pyramid is a polyhedron in which one face, the base, is a polygon and the other faces, which are lateral faces, are the triangles that meet at a common point known as the vertex. And we name the pyramid by the shape of its base. In the diagram, I have a pentagon as the base. Therefore, this is a pentagonal pyramid. The base is identified as the pentagon. The intersection of the lateral face and the base creates a segment known as the base edge. The intersection of the lateral faces, which are triangles, creates a segment known as the lateral edge. And of course, the faces intersect at a point known as the vertex. The height of the pyramid, which we call h, is a segment from the vertex that is perpendicular to the base, and that is the height of the entire pyramid. The height of each lateral face is known as the slant height, or labeled L. It is a segment from the vertex that is perpendicular to the base edge of that lateral face. A regular pyramid is created when the base of that pyramid is a regular polygon. Recall that a regular polygon is a polygon that has all sides congruent and all interior angles congruent. And that would make the lateral faces isosceles triangles. Here I have a net of a regular pyramid. In this case, this would be a square pyramid because the base is a regular polygon, which is a square. Therefore, the four triangles in the diagram are four congruent isosceles triangles. Recall that an area of a triangle is 1/2 the base times the height. Here the base would be the segment of the intersection of the lateral face and the base, and the height is the slant height known as L. And we also know that the perimeter of our base is 4s, 4 times the measure of one side of my polygon. The area of this regular pyramid, therefore, would be the area of the triangle or lateral face is 1/2 the base, which is s, and the slant height, which is known as L. In this case, we have the area of a triangle equal to 4 times that amount because I have 4 lateral faces that I know to be congruent. If I use the commutative property, move that 4 adjacent to the s, that gives me 4s. But recall, we know that 4s is equal to the perimeter of my base. Therefore, I can substitute in p for 4s, and that gives me the lateral area of my pyramid, which is the surface area of each lateral face, to be 1/2 p, which is the perimeter of the base, times L, which is the slant height of the lateral face. Therefore, Theorem 11.3, which is the lateral and surface areas of a regular pyramid, are stated as the lateral area of a regular pyramid is half the product of the perimeter of the base times the slant height. Therefore, I have the lateral area equals 1/2 PL, as identified on the previous slide. The surface area of a regular pyramid is the sum of the lateral area and the area of the base. Therefore, the surface area is the lateral area, which is identified above, plus the area of the base, which is identified as B. B equals the area of the base, which we know would be S times S on the previous page. In the diagram, I have a cone. A cone is a figure that has a base in the shape of a circle, and its sides intersect at a point known as the vertex. The altitude of the cone is the height of the cone, known as h, and the altitude is a segment from the vertex to the center of the circle, or center of the base, and is perpendicular to the base. L is the slant height of my cone. It is a segment from the vertex to a point on the circle itself. And when the altitude is perpendicular to the base, it is known as a right cone. Theorem 11.4, lateral area and surface area of a cone. The lateral area of the right cone is half the product of the circumference of the base and the slant height. Here, lateral area equals 1/2 times 2 pi r, which is the circumference of a circle, times L. Or LA, which is the lateral area, equals pi RL, because 1/2 times 2 is just 1, leaving us pi RL. The surface area of the right cone is the sum of the lateral area and the area of the base. Surface area equals lateral area, identified above, plus the base. Here, the base is b, and the base is equal to the area of the circle, which we know is pi r squared. Find the surface area of the pyramid to the nearest whole number. In the diagram, I have a pentagonal pyramid. I know that because the base is a five-sided object. It's a regular pentagon, and I need to use the surface area formula from the previous slide to determine the surface area of my pyramid. Recall from that formula, I have 1/2 the perimeter P of my base, which is 5 congruent segments of a length 12.58. So I have 5 times 12.58 times L, which is the slant height of my lateral face of my pyramid, which I know is 16. Now I need to determine the area of my base. If I would complete a segment from the center to another base vertice, you can see I'm given one triangle. I can determine the area of that triangle by the formula 1/2 base times the height, which is given to be 5 square roots of 3 centimeters. And if I complete the segments to the vertices, you can see that I will generate 5 congruent triangles in my pentagon. 1, 2, 3, 4, 5. Therefore, I have the area of one triangle equal to 1/2 the base times the height, which is 1/2 12.58 times the height, which is 5 square roots of 3. But I have 5 congruent triangles. Therefore, that is the area of my base. Now, when I plug that into my calculator, I'm going to get 775.56. When I round to the nearest whole number, I get 776 centimeters squared. On this example, I need to find the lateral area of each pyramid to the nearest whole number. Here, I'm given a square pyramid. The base is a regular polygon, and here it is square. Therefore, each base edge is 6 meters. I need to substitute known values into my lateral area, which is known to be 1/2 P, which is the perimeter of the base. Therefore, I know I have 4 times 6 for the perimeter of the base, times L, which is the slant height of one of my lateral faces. I have to determine the slant height of my pyramid. To do that, I create a segment between my slant height and the intersection point of my altitude. That will generate a right triangle. Since this is the midpoint of my base edges, I know that this segment on the base itself is 3 meters. And I do know the altitude of my pyramid. Therefore, all I need to do is use the Pythagorean theorem to generate that hypotenuse, which is the slant height, or L, in my formula. When I do that, I know the Pythagorean theorem is a squared plus b squared equals c squared. Substituting in my known values, which is 3 and 10, I get 9 plus 100. Therefore, c squared is equal to 109. The square root of both sides is 1044. Therefore, when I substitute in, I'm going to get my lateral area to equal 1/2. P is 4 base edges times the length of each base edge, which is 6, times the slant height, which I know to be 10.44. When I substitute that into a calculator, I'm going to get 125.28. Rounding to the nearest whole number, I'm going to get 125 meters squared. Here they want me to find the lateral area of the cone to the nearest whole number. I'm given a diameter of 14 meters and an altitude of the cone, which is 18 meters. The formula for lateral area of a cone is 1/2 times 2 pi r, which is the circumference of the base, times L, which is the slant height of my cone. I know that the altitude is a segment from the vertex that is perpendicular to the center of the base. Here, I know that this is a right angle. Therefore, I generate a right triangle with my radius, which I know is 7, and the altitude, which I know is 18. And by using the Pythagorean theorem, I can generate the slant height of my cone. Using the Pythagorean theorem, I'm going to get a squared plus b squared equals c squared. Substitute in. The radius of my circle is 7. The altitude is 18. And therefore, when I substitute it in the calculator and take the square root, I get c, which is the slant height, to be 19.3. Now I substitute that into my lateral area formula, and I get 1/2 times 2 times pi. The radius is 7 times L, which is my slant height I just determined to be 19.3. Plugging into a calculator, I get 424.43. Rounding to the nearest whole number, I get 424 meters squared. Here they want me to determine the surface area of a cone in terms of pi. Recall the surface area is equal to the lateral area plus B, which is the area of the base. To determine the lateral area, I need the slant height of my cone. Here I'm given the altitude, which is a segment from the vertex that is perpendicular to the base. Therefore, I know the altitude generates a right angle with my radius. That gives me a right triangle, and I can determine the value of my hypotenuse, which is going to be the length of my slant height. Therefore, I just substitute into the Pythagorean theorem. A squared plus B squared equals C squared. Therefore, my radius is 12. My altitude is 15. When I substitute in a calculator and take the square root, I'm going to get C equal to 19.21, which is L, my slant height of my cone. Substituting into my formula, I'm going to get my lateral area to be 1/2 times 2 pi r. R is my radius, and 2 pi r is the circumference of my base. L is 19.21, just calculated, which is the slant height of my cone, plus B, which is the area of my base, which is pi r squared, and r is 12. Substituting the values into my calculator, not pi because I'm solving in terms of pi, I'm going to get 230.52 pi and 144 pi. Combining like terms gives me 374.52 pi inches squared for my surface area of the cone. My last example, the lateral area of a cone is 480 pi millimeters squared. The radius is 120 millimeters. Find the slant height. To do that, we're going to use the lateral area, which is 1/2 times 2 pi r times L. When we simplify 1/2 times 2, I'm going to be left with pi r L. Substituting in the values for lateral area, 480 pi millimeters squared equals pi. R is given to be 120 millimeters. We have to determine L. So when we substitute in LA, 480 pi millimeters squared, pi, R is 120 millimeters, and L comes down. When I divide both sides by 120 pi millimeters, I'm going to get 480 divided by 120, which is 4. Pi over pi cancels out. Millimeter squared divided by a millimeters gives me millimeters, period. So my slant height is 4 millimeters.